Hi everyone, welcome to lecture 11 on Goodman's paradox and the uniformity of nature. The objectives for this video are the following. After watching, everyone should be able to, number one, explain using an example how for any prediction one can find a regularity whose projection licenses that prediction. And number two, explain what our discussion of regularities and projections allow us to infer about the principle of the uniformity of nature. So last time we looked at Goodman's paradox. The paradox was that projecting unprojectable regularities might lead to a prediction that conflicts with a legitimate prediction that's made by projecting a projectable regularity and from the same set of data. The situation, though, is arguably even worse than this. In fact, given any prediction whatsoever, you can kind of manufacture a situation in which you can find a regularity that licenses that projection. So given any prediction you want to make, you can give an argument such that the regularity in the premises licenses your prediction. The point is that some of these regularities shouldn't be projectable according to scientific inductive logic. We shouldn't be able to just predict anything we want. And this is bad news for any hope of a system of rules for inductive logic. Now, the book gives 3 examples of how you go about doing this. We're going to walk through the third example in this lecture video. There will be questions on the assignments that relate to the other 2 examples, so it's important to have a read of those because they'll help with the questions. So here is that third example. Often we see tests that are used that contain problems involving a sequence of numbers, and they ask people taking the test to continue the sequence. So here are 3 sequences, for example. We've got the first one that starts 1, 2, 3, 4, 5, the second one which starts 3, 6, 9, 12, 15, and the third one which starts 3, 7, 11, 15, 19. Now, when asked to continue each sequence, there's a natural answer to give for each one by spotting the pattern in each sequence. So here's an easy question in the interests of having a go yourselves. The next term in the first sequence is obviously 6, you might say, because you just add 1 each time. And similarly, the next term in the second sequence is obviously 18, because you add 3 each time. And the next term in the third sequence is obviously 23, because you add 4 each time. Now, if we say all that a bit more precisely, then you would reason in the following way. These sequences are all arithmetic, which means the difference between each consecutive term is constant. Now there's a formula for calculating the nth term in an arithmetic sequence, and it's called the generating function of the sequence. And it's this, a1 plus n minus 1d. This is a function of n. A1 is the first term in the sequence, and d is the common difference between the terms. So a more precise line of reasoning to determine the 6th term in each of these sequences would be to determine the generating function for the sequence and ask it what the 6th term will be. Now don't worry if this all looks a bit abstract so far, we're going to look at some examples. So let's do the generating function for the first sequence. We're interested in the 6th term, so what happens when n equals 6? The difference between the terms in this sequence, so 1, 2, 3, 4, 5, is just 1 because you add 1 each time. So d equals 1. The first term in the sequence is 1, and so a1 is 1 as well. So the generating function is 1 plus n minus 1 times 1, which simplifies to n. The generating function gives us the 6th term when we substitute n equals 6 into the function, and when we do that we get that the 6th term is 6, which is just what we said before. Now let's do the same thing for the second sequence, so 3, 6, 9, 12, 15. Here the difference between the terms is 3, so d equals 3. The first term is 3, so a1 is 3 as well. And so the generating function for this sequence is 3 plus n minus 1 times 3, which simplifies to 3n. And when we substitute n equals 6 into the generating function to calculate the sixth term, we find it is 3 times 6, which is 18, which is what we said before. And finally, let's do the same thing for the third sequence. So the difference between the terms is 4 this time, so d equals 4. The first term of the sequence is 3, so a1 equals 3. And so the formula gives us 3 plus n minus 1 times 4, which simplifies to 4n minus 1. And when we substitute n equals 6 into the generating function to calculate the sixth term, we find it is 4 times 6 minus 1, which is 23, which is what we said before. So what we've done, perhaps a little laboriously, is find the regularity in each of these sequences by finding a generating function that yielded all the given members of the sequence, and then we projected that regularity using the same generating function to give the sixth member of each sequence. For example, for the first sequence, this just amounts to us making the following argument. For every given member of sequence 1, the nth member of the sequence was n. Therefore, for the next member of sequence 1, the nth member will be n. But there's a problem. We spotted a regularity in the generating function we identified that fits the first 5 terms of that sequence, sequence 1. They were 1, 2, 3, 4, and 5. But this regularity is not unique. Here is another generating function that also fits the first 5 terms of sequence 1. That's g of n down at the bottom there. And that's n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5, all plus n. Now I'll leave it to you to check that substituting n equals 1 all the way up to n equals 5 gives you 1, 2, 3, 4, and 5 respectively when you plug those into g of n. But when we substitute n equals 6 into g of n, that generating function at the bottom, it yields the number 126, not the number 6 like the other function, f of n, gave us. And indeed, it's a mathematical fact that no matter what number you pick to continue the sequence 1, 2, 3, 4, 5, there is a generating function that fits the first 5 numbers and yields whatever chosen sixth number you've picked. So, although we thought we'd spotted a regularity that we think looks projectable, there are regularities that fit the initial pattern, 1, 2, 3, 4, 5, such that projecting those regularities gives you any number you want as the sixth number of that sequence. So actually, if you were asked to do this on a test to continue this sequence, there's an argument you can make such that any answer you put down should be correct. So in this spirit, have another go at the question I asked you earlier. Now, of course, what we've learned is that, in fact, any of those answers you just saw are technically correct. So no matter what you put, you will have got a point. Now, the point of all this is the following. To say that valid predictions are those based on past regularities, without being able to say which regularities, is pointless. Regularities are where you find them, and we've seen that you can find them anywhere you like. So, a characterization of scientific inductive logic as a system that projects observed regularities into the future is pointless, or it's trivial, unless we can say what the projectable regularities are. Now, finally, we said we'd link our discussion of regularities and projections to the principle of the uniformity of nature, and the link is found in the analogy between the two. So just as we said a second ago that a characterization of scientific inductive logic as a system that projects observed regularities into the future is pointless unless we can say what the projectable regularities are, the idea is that a characterization of scientific inductive logic as a system that relies on the uniformity of nature is also pointless or trivial unless you can say in what respect nature is uniform. Let's think back to the Goodman paradox from the last video. There we saw that the human who thought all observed emeralds have been green in the past and that the future would resemble the past in this respect predicted that the emerald would remain green. That is, the human presupposed that nature was uniform with respect to the greenness of emeralds. On the other hand, the alien, who thought all observed emeralds have been grue in the past and that the future would resemble the past in this respect, predicted that the emerald would remain grue. The alien presupposed that nature was uniform with respect to the grueness of emeralds. Now, these predictions of the human and the alien we saw contradicted one another. So the future cannot resemble the past in both the sense that the human thought it does and that the alien thought it does. So the point is, nature cannot be uniform in every respect. But what we've seen in this lecture is that it's no use to weaken the claim nature is uniform in every respect to the claim that nature is uniform in just some respects. Because of course nature is uniform in some respects. What we've seen in this lecture is that given the sequence beginning 1, 2, 3, 4, 5, we can find a uniformity that licenses the prediction of any number we want as the sixth member of that sequence. So to say nature is uniform in some respects is just unhelpful if we're to use the uniformity of nature to develop a scientific inductive logic. Then we must be able to say in precisely which respects nature is uniform. Or on the other side of the same coin, we can't say that every regularity is projectable, and it's trivial to say that some regularities are projectable. We have to be able to say which ones, so which regularities are projectable. So, we've seen that there are so many regularities in any sequence of observations and so many ways for nature to be uniform that saying things like scientific induction projects observed regularities into the future or scientific induction presupposes the uniformity of nature, those things just lose all meaning. They just aren't going to help us construct a system of scientific inductive logic that does what we want it to do. Solving this problem, saying exactly what regularities are projectable or saying exactly in which respects nature is uniform, is what's called the new problem of induction. Now, unfortunately, I don't have the answers, so we'll leave our philosophical discussion of the last few weeks here. The next topic we'll look at is the experimental method, and in particular giving an analysis of causality that explains some features of the experimental method, which will eventually lead us to this thing called the probability calculus. So have a go at your reflection questions, and I'll see you all next time.